So I've started the recording. Let's wait for, say, a couple of minutes for everyone to join. Yeah, so if both of you have any questions, you can ask me until. Anything from the lectures, anything from the previous tutorials. Yeah, Divyanshu, you do not understand the Reynolds transfer theorem. Okay. Yeah, so today we'll discuss about it. Not going to derive it, but I'll explain you what it implies. Okay. Okay, so I guess I'll keep checking in when people join. We can start the session. So today we'll discuss about Reynolds transport theorem. And if you have any questions in between, just stop me and we'll discuss it more in detail. Now, at the outset, let me say Reynolds transport theorem is useful when you want to study what is the relation from the system's perspective, control mass perspective and control volume perspective. So first, can you tell me what is control mass versus control volume? Yes, anyone? Yeah. Mass is conserved, okay. And in control volume, the mass may or may not be conserved, but the volume needs to be conserved, right? Yeah, exactly. And in control mass, volume need not be conserved. Okay, so here the point is that mass is conserved, okay, and in this case we say that it is important that we take a conserved volume. Mass, energy, all these things need not be conserved. So for example, let's say I have this particular object, it's a system, and let's say that there is some fluid inside this, but there is also flow. Okay, so what I've drawn is stream lengths, so there is flow, and at any time instant if I consider this fluid blob, at the next time instant what will happen? It is possible that this is at time t, and at the next time instant what you see is that the okay, so first let me copy the same picture for you. Now at the next time instant it is possible that this control mass, okay, so this is your control mass, its shape has changed, okay, its shape has changed completely, and the volume, uh, so what I'm conserving here is mass, the volume has changed, and the mass is conserved in this region. Okay, and there is flow. So when the fluid is moving, when there is flow, you need not be able to conserve control mass. But we know how to write, let's say, Newton's law for a control mass system from the control mass perspective. How do we write it from the control volume perspective? So that is the question that we are trying to answer, and that's where Reynolds transport theorem comes handy. Okay, so let us um, consider any quantity. Any quantity I am going to denote as n, but examples are, let's say, mass. Okay, what other quantities can be conserved? What are the other quantities that we usually want to study? Momentum. Yes, so let me write momentum. Okay, mass, momentum, energy. So these are the quantities that we want to conserve. And if I'm looking at just a ball, let's say there is a solid ball, and I tell you that we have imparted it some velocity v, you know that it is going to move in a projectile motion. Okay, so you can solve for this projectile motion because you know that the shape is not changing, it is a control mass. You can apply Newton's law, and you can find how the momentum conservation works over here. Okay, but what about a fluid? How do we do this for a fluid system? So that's where Reynolds transport theorem comes. Okay, so I'm going to consider any of these quantities, and I'm going to denote, let's say, mass, momentum, energy, everything as n. Now one thing you must have studied, there is a difference between intensive and extensive quantities. So can you tell me what is the difference? Yes, anyone? Yeah, someone was trying to say something. Mm-hmm. Yes. Okay. Yes. Yeah, that's a very nice example of kinetic energy. Uh, Someone is trying to join. Okay. Yeah, so kinetic energy is extensive because it depends on mass. So if there is dependence on mass, then it is an extensive quantity, else it is intensive. So if I am talking about energy, energy of a system depends on the mass. How much mass is there, that changes the energy. But on the other hand, if I ask you what is the energy per unit mass, then that becomes an intensive quantity. Okay, similarly, if I go back to these examples, so mass itself is of course dependent on mass, so it's extensive. Then the momentum is mass into velocity, that is also an extensive quantity. Energy is also an extensive quantity, right? So for consistency, let me write this as capital E. Okay, so anytime I can relate the extensive quantity n to some intensive quantity eta being multiplied to the dm mass, right? Okay, so whatever is the mass of the system, like I wrote here, energy per unit mass, or I can say that energy is actually this energy per unit mass into dm integral over the entire mass of the system. Okay, So similarly, I am going to denote n as integral eta dm. And what is dm? So this is integral over the mass of the system. But remember what we were trying to do? We were trying to relate the control mass and the control volume. So the relation is very simple. dm can be written as rho dv, and now instead of integrating over the mass, we integrate over the volume of the system. Okay. Is this part clear? Okay, so this was our new blob after time. So this is at time t plus dt. So we started at time t, we had some fluid blob, and then at time t plus dt we had this new position, new volume of the fluid blob. So let us divide this into some 3 regimes. Let's say I have so let's have this common regime, okay, and I'm going to call it 2, whereas let's take this region and let's call this 1, okay, and finally let's take this region and call it 3. So whatever is the overlapping region between this time instant t and t plus dt, that is the only region where there is any overlap. So we are going to call it region 2, and these are 1 and 3 regions. So what we can do now is we can solve for what happens in time. So we can start by asking if there is a change in n. If there is a change in n, that is the control mass perspective, right? So if you were looking at this example of the ball which is moving, so you can ask what is the dv by dt, or what is the d momentum, d by dt of the momentum, and simply by Newton's law you can derive the rate of change of momentum. But here it is not that simple, because the volume of the object is also changing, and that's why we need to solve in this format. Okay, so now the question is, what is d by dt of this quantity n for this system that we have considered? Okay, so this is since one of you said you have not understood Reynolds transport theorem, let me show you a quick way of deriving this. I'll not go into details, but this is how you would arrive at the Reynolds transport theorem. So what we are going to do is, in maths, basic maths you would have seen, if I take the limit delta t tends to 0, I can write the derivative as n at time t plus dt minus n at time t, okay, divided by dt, delta t. Okay, and this is the limit delta t tends to 0. So this is very straightforward. Now what is n at t plus delta t? So go back here. If this was the original thing that I started with, this was n, right? So I can now divide n at t plus dt as n in the region 1 plus n in the region 2. Just okay, so if we look at this picture, this is the blob at t plus dt, right? So n at t plus dt comprises of region 2 and region 3. So I can write this as n at region 2 plus n at region 3, whereas n at time t is n at region 2, that is common. Okay, so if you see here in this picture, it is common, and n at region 1 is the additional. This is clear? I hope this is clear. Okay. So if this is understood, now what we will say is we are going to consider a control volume. Okay, I am going to observe a control volume, and the control volume is such that there are regions, we have regions 1 and 2 which together make up for this n at t, and there are regions 2 and 3 which together make up for t plus dt. So region 2 is the location of the system. This region 2 is the location of the system, so I am going to call this as my control volume. Okay, so we can now write so at t plus dt you can see that the system is now located in this region. So I am going to write this as n control volume minus n1 plus n3. Is this clear? If there is any question, you can ask me now. If it's clear, just please speak up that it's clear. Are you guys following this? It is clear. Okay. Okay, so then what we do is we put these back into the equation. Let me again add a page here. Okay, so now we just put this back into our equation of dn by dt, and we can arrive at this equation dn by dt of the system, which is our control mass perspective. This is equal to, so again this is what? This is NCV, remember N2 is NCV, plus N1. So you get NCV at t plus delta t minus N1 plus N3 minus NCV at t. Okay, and this entire thing is divided by delta t in the limit delta t tends to 0. Oh, and we also have a plus n1 over here, so we also have a minus n1. Okay, so you can now rewrite this as limit delta t tends to 0 NCV at t plus delta t minus NCV at t. Yes, somebody has a question? Okay, plus you have N3 by delta t and minus N1 at delta t, and these are also in the limit that delta t tends to 0. Okay. Any questions till here? Okay, so now clearly what is this? Yes. What I took as control volume is the region which is not changing from t to t plus dt. Okay, so this is the region 2. What I am showing you is one simplified derivation. There are other ways of deriving the Reynolds transport theorem. Okay, and if you want to refer to this derivation later on, let me also tell you, you can refer to Fox and McDonald's and chapter number 4. Yeah, so moving on, what is this term? In the limit delta t tends to 0, this is the derivative of NCV, remember? So on the left hand side, we already have this dN by dt from the control mass perspective, systems perspective. And we have on the right hand side our first term, which is d by dt, or may I write it as, because it is only with control volume, so I am going to write it here as dou by dou t of NCV, plus we have some other terms. Okay, so what are our other terms? We have the limit delta t tends to 0, we have the N3 term minus the N1 term divided by delta t. And what is this term? So NCV is N contained in the CV, in the control volume, and that is what we wrote over here. Okay, so we can replace this term alone as dou by dou t integral eta rho dv. Okay, integral over the volume of the system. Now we have to evaluate these terms. So let's go back. What is N3 actually and what is N1? N1 is where the system was at t. N3 is the new position of the system. Okay, so there is a movement from 1 to 3. There was a movement. So there is actually, you can look at it from another perspective. Now imagine that the only thing you are concerned is region 2, and in region 2 everything remained the same, but whatever was in region 1 has gone to region 3. Okay, so there was a flux from region 1 to region 3, and it went through the region 2. Okay, so there all this mass or all this quantity n in region 1 moved into region 2 and then moved out of region 2, and it formed what we now know as region 3. Okay. So this term actually implies flux of quantity n through region 2. But what was region 2? Region 2 was my control volume. So what this term actually implies, if I have a control volume, okay, so there was some flux from here and outward flux here, and what is this? This is the control surface, right? So it actually implies flux via the control surface. Are there any questions about this concept? Okay, so this is the part where how we get to the flux term. I'm not going to derive it, but it is pretty simple. What you need to do is you need to basically take a region, take the area vector, right? So if you have some region, you have some area vector, right? Area vector is nothing but the total area multiplied to the normal vector, and there is fluid flow. This is some streamline, so you can always draw the tangent to this streamline, which will give you the velocity vector. And what is the flux? Flux is whatever is your quantity, it is moving across the area because of the velocity. So you will always find the flux is A dot V, multiplied to the quantity. So the quantity is eta into rho. Okay, and this has to be integrated over the entire area. So what you can do is take an elemental area and take the elemental area dA and integrate this. So this is essentially the flux. Okay, so now we can write our equation dN by dt for the control mass is equal to dou by dou t of integral eta rho dV, this is integral over the volume, plus this flux term which came from here, so that is integral, the same thing I am going to write here, eta rho V dot dA, and the integral is over the control surface of the control volume that we have considered. This is our Reynolds transport theorem. And from the Reynolds transport theorem, you can go ahead and derive your conservation of mass, conservation of momentum. It is just one line derivation. So if I want to talk about mass, okay, so N is equal to M. What is eta? If N is equal to M, what should be eta? 1. Eta is just 1. If you put this in your equation, what do you get? You get dm by dt is equal to dou by dou t of rho dv plus integral rho v dot dA. Isn't this your continuity equation? Yeah, this is something you are familiar with. Okay, so any questions about the Reynolds transport theorem now? Divyanshu, you had doubts. Do you still have doubts or everything's clear now? Okay. So we will solve some questions with RTT. Maybe that will help you clear the doubts. You have a question saying here in this case density may change. Can you please speak up and tell me what is the question? Where is your doubt? Yes. Well, not necessarily, only if see, this is a very general derivation. Now if you keep density as constant, just take density out of the derivative, right? So if it is in fact, let's discuss the case when it is an incompressible flow. So what happens if it's an incompressible flow? Okay, so this is a special case. Now here we have not made any assumption whether density is constant or not, whether it is incompressible fluid or not. We have not made any assumption. Okay, and this is my Reynolds transport theorem. Okay, so the special case, let's discuss. If we have incompressible flow, so then I can take density out of the integral, right? So let me write, let's say, for our continuity equation. Okay, and if I take density out, we have dou by dou t of the integral of the volume. Okay, plus again density, it's just a constant, so I can do this v dot dm, and this is equal to dm by dt. else can I say about this? If there is an incompressible flow and there is mass conservation, and let's say dm by dt is 0, why are we assuming dm by dt is 0? Yes? Don't know. It's an incompressible flow, right? So there's no change in mass and there's no change in density. And this, what does this term become? So now this rho and rho, I'll just take it out. This is nothing but dou by dou t of the total volume plus v dot dA integral, and this is equal to 0. Okay, so now density plays no role. What about dou by dou t of volume? Let's say I have a system where you cannot change the volume. Okay, so for example, if you have a flow through a pipe, okay, so let's say you have as an example, flow by a pipe. Okay, so no matter what, your fluid is going to go in this pipe, it is going to fill throughout the pipe, the volume is not going to change. Okay, so if we have some rigid volume boundaries, then I can say that dou by dou t of V is also equal to 0. Your control volume, total volume is not changing. So the only term that survives is V dot dA integral is 0. And this is throughout the control surface. Okay, so whatever flows into this control volume will exit this control volume, and that makes sense because this is an incompressible fluid. If it was a compressible fluid, then whatever goes in, m dot in and m dot out, will not be equal because some mass can be contained within and the density is changing. Is this clear? And this also you have seen earlier when we have incompressible flow, we used to conserve a quantity called flow rate, right? So the flow rate Q is equal to nothing but integral V dot d. Okay, so I hope that answers your question. And then you have asked, is RTT applicable where the mass of fluid is constant but volume is changing with time? If the mass of fluid is constant, then you should ideally use the control mass perspective. But if you want to use the control volume perspective, yes, of course, because in our equation, see, we have rate of change of volume. Rate of change is the control volume that you have considered. You have that term in your Reynolds transport theorem. See, what this theorem does is it simply relates, if I solve in the control mass, what do I get? And if I solve in the control volume, what do I get? That is the simple relation. Okay, you can either use the left hand side perspective or the right hand side perspective. So for example, if I now take momentum, so on this side you just have d by dt of momentum, and on the right hand side you have rate of change of momentum in control volume plus you have momentum into rho into v dot dA. So if you go back to your momentum equation, what we are using over here, this is the rate of change of momentum of the control volume or the control system, but What causes that rate of change of momentum? That does not come from the Reynolds transport theorem. What causes change in the momentum? If there is some force applied, if there is some pressure change, right? Okay, so that will come from the physical conditions. What are the forces, or what are the viscous forces, external forces, pressure change? All these things will cause change in momentum. Once the change in momentum is caused by external factors, whether we study it from the control mass perspective or the control volume perspective is our choice, and we have a way to relate them, and that is Reynolds transport theorem. Is that okay? Okay. Okay, so then let us solve some questions. Okay, so the first question, we have flow through a pipe where there is a junction of pipes, and as you can see, there is fluid coming in through 1 and moving out from 3, and also through 2, and then there is this hole. Okay, there's a hole which is labeled as location 4. So consider a steady flow in a water pipe joint which is shown, and the areas are given to you. In addition, we have fluid lost through the hole at 4, and the rate of this loss is also given. So that is 0.1 meter cube per second. So what we need to find is the average speeds at section 1 and 3 are given, v1, v3. So we know v1 over here, we know v3 over here. We have to find velocity at section 2. What is v2? Okay. Now this is the example of rigid control volume boundaries, and that's what just now we looked at. If you have flow through a pipe, it is a rigid volume boundary, and this dou v by dou t term becomes 0 in our Reynolds transport theorem. So if I have to use my Reynolds transport theorem, and from that I have derived my rate of change of mass, and from there we apply the condition of rigid volume boundaries, what we are left with is that the total integral of rho v dot dA is equal to 0. Okay, and we are now going to make the assumption that this is an incompressible flow. So with the assumption, assume incompressible flow. We can just ignore density, and instead of integral I can take a summation, because see, what I need to do is consider the control surface. Remember, the integral is over the control surface. So what are my surfaces? So let us first draw our control volume. I am going to consider this, these are my borders of the control volume. Now there is no flow through these curved borders, right? There is no flow over here. So the only flow I need to worry about is through this control surface, through this control surface, and through this control surface. Okay. So I am going to do a summation over the control surfaces and say v, velocity into the area, v dot a is equal to 0. So we know the areas, so we can write v1 and again v dot a. So what is v? How do we find the dot product here? The flow is normal to the surface, so the dot product, the it is va into cos theta. So cos theta is just 1 if the flow is normal to the surface. Okay. So v1 into a1 plus v2 into a2 plus v3 into a3 is equal to 0. Now always remember that if you have considered a surface and your n cap is in this direction and your velocity is in this direction, then we can take it as positive velocity. If you have a condition where n cap is in this direction but the flow is in this direction, then we will take it as negative. Okay, and always we take n cap outwards to the surface. So in this case, if I draw the n cap, so this is n2 cap, this is n3 cap, and this is the direction of n1 cap. So can you now tell me V1 A1, is it positive or negative? It is negative, right? Yeah, so let me be careful and still write the dot products here. Yeah, and now we have minus V1 A1, and with what I have drawn, is V2 N2 positive or negative? It is negative still. Okay, and V3 A3 is positive. Okay, and this is equal to 0. Yes. Oh yeah, I forgot. Okay, yeah. Plus there is also V dot A through the hole. Thank you. Completely forgot the hole. Fine. So what about the hole? So the velocity is, of course, it is outwards, and n cap is also outwards, right? So this is going to be, we know the rate already, so it is, I can write it as q hole, and it is positive according to our convention. Why have I written q? Because what is given to us is 0.1 meter cube per second. It's already v into a is what is given to you. Okay, so now let us put in the values. So q hole is 0.1 minus v1 is 5 into a1, which is 0.2, minus v2, which is what we have to find, a2 is 0.2, plus v3 is 12, and a3 is 0.15. So the only unknown is v2. Please solve and tell me what you get as the value of v2, and whether it is positive or negative. Positive 4.5 meter per second. Okay, yeah, that's right. So I assume that v2 is going inside into this surface. That means there is an inflow from pipe 2. Okay, so I assumed this and it came out to be positive, so my assumption was right. If it came out to be negative, then it would have been an outflow. Okay, so this question is fine. I hope everyone got this answer. If you have any questions, you can ask me now. Okay, so we can move on to the next question. So there is a fluid which is in direct contact with a stationary solid boundary, and see, when there is flow over a solid boundary. Let's say you have uniform flow and you keep a plate or some obstruction in between. So there will be viscosity, and because of viscosity or friction, because of friction between the flow and the solid boundary, you'll see that the flow profile, the velocity profile changes. So what is drawn here is the free stream velocity, and what is drawn here is the velocity because of the boundary layer. Okay, and as you move further along the plate, actually this boundary layer thickness increases, and then after a while it just almost saturates. So this boundary layer thickness is denoted as delta at any location. So at this location also it is denoted as delta. So delta is a function of x. This is my x direction, and at any point I can draw the velocity profile. So the velocity profile u is in fact a function of y. As you can see, with y it is changing, so it is a function of y, and it is also function of this delta. Okay, so and there are theories, so it has been proven that u is actually function of y by delta. Okay, so what you are given is that a boundary layer is formed. The flow ahead of the plate is initially uniform with some velocity capital U, and the velocity distribution within the boundary layer is given to you as an approximation. So this is the function. U is the velocity at any location, but it is normalized with the free stream velocity capital U. Okay, and that is given as a function of y by delta. Boundary layer thickness at some location. So at this location D, the boundary layer thickness delta is given to you 5 mm. The fluid is air. Assuming the plate width is perpendicular to the paper, so that's into the paper, you have some width of 0.6 meters. We have to calculate the mass flow rate across the surface BC of the control volume ABCD. Now first let us understand what is happening over here. So if you look carefully, we have drawn this control volume, okay, and what is given to you is that there is some influx, there is some outflux. Now clearly flow cannot move in this direction, right? There is no flow in this direction. Why? Because there is a solid, rigid boundary. So the flow cannot penetrate this boundary. And if there is any imbalance, what comes in through this control surface and what goes out of this control surface, if they are in imbalance, then either the density here will change, or what will happen, that fluid has to move out of the control surface BC. Okay, and given that this is an incompressible flow that we are dealing with, whatever imbalance happens, whatever is the influx at AB minus whatever is the outflux at CD, that will be balanced by the outflux or influx at BC. Okay, and that is what we have to find. So how do we do this? Now this is exactly what the Reynolds transport theorem states, that if there is any quantity which is moving past a control volume, there is some influx, some outflux, then we can relate the change in the total quantity to the change through the control volume, right? And here the quantity that we are concerned with is the mass, or the not the mass. We have to find the velocity distribution. Yeah, so we are concerned with the mass because there is some mass influx and some mass outflux. Mass cannot accumulate over here, so it has to move out of BC. So there will be some movement out of here, and there will be a velocity with which the fluid moves across BC. So that's the velocity we have to find. Is this clear? Any questions on the problem setup? Okay, so if not, now we have taken a rigid control volume ABCD, and going back to the equation that we just derived over here. Yep. So if we have a rigid control volume, we can forget this term, and the only term we have to be concerned about is V dot dA integral. Again, because it is incompressible, I can remove density from the equation. Okay. So let us first write what we need to solve for. Across all the control surface, we have V dot dA equal to 0. What are all these surfaces? AB, AD, DC and BC. Right, so I can write integral over AB plus integral over CD plus integral over AD plus integral over BC, and this will be 0. Now what about integral over AD? Why? There is a solid boundary, and what are we actually integrating? We are basically saying V dot dA, right? So here in this case, your velocity is 0. Okay, so if the velocity is 0, then this entire integral drops to 0, and this is what I need to find. And for AB and for CD, we know the velocity profiles, so we can do the integration. Okay, so let us first look at the AB term. AB, integral over AB V dot dA. What is that? So if I look at AB, you see what is coming in is just uniform flow, right? So just uniform flow, and always draw the n cap vector perpendicular, right? Perpendicular to the surface and outwards. So what is outwards over here? Outwards is in this direction. Here it is in this direction. Here it is in this direction. So I can say that your n cap is in fact minus x cap, and your velocity is nothing but u in x cap. So what is your V dot dA now? And what is the length of AB, by the way? Go back to the picture. It is the same as CD, and what is given to you is that at this location there is some width of the boundary layer, delta. So it is some delta equal to 5 mm. So I am going to fix this length as delta. So now what is V dot dA integral? Velocity is constant u x cap dot minus x cap. Area is dA vector is the area into n cap. So I have only written n cap. What about the area vector? Yeah, width of the plate and into dy, right? And if I integrate this, it has to go from y equal to 0 to y equal to delta. Now everything is constant, so I can evaluate this integral easily. U, there is a minus sign, w, and integral y from 0 to delta is just delta. Okay, so this is the integral over the control surface AB. Okay. So now let us evaluate the integral over CD. Again, this is b dot n cap dA integral. Now at this point, at this location CD, the velocity has a certain profile, and that profile is given to you, right? So at this location, I can say the velocity has a certain profile, and I am going to write that in these terms. So velocity is nothing but this u. So I'll take capital U on the other side. So capital U multiplied to whatever is this function given to us, 2y by delta minus y by delta whole square. So this is my velocity, and it is in what direction? It is in the positive x cap direction. Okay, so this is u 2y by delta minus y by delta whole square in positive x cap, and n cap is in what direction? N cap is also in positive x cap direction. See, taking your n cap in the right direction is very important. So this is a very common mistake that people make. At the surface AB, n cap was in minus x cap, because you always take normal outwards of the control volume. So here it is in minus x cap, here the n cap is in positive y cap, here the n cap is in positive x cap. Okay, so that's what we have written here. V dot n cap dA integral can now be written as u 2y by delta minus y by delta whole square. So V dot n cap, you can see it is x cap dot x cap, that leads to just 1, so I am not writing that. And dA, like you said earlier, it is w into dy. Okay? W into dy integral. So I can take w and u outside, and this is integrated from 0 to delta. So can you please evaluate and tell me what is the integral? Please evaluate this expression and tell me the answer. Check again. So you put the limits 0 to delta. See, first you should have gotten this expression, y square by delta minus y cube by 3 delta square. Get 2 by 3, not 1 by 6. Okay, so this is the value we get from control surface CD. So going back to our original equation, what do we have? Integral over AB plus integral over CD plus integral over BC is equal to 0. So let us take these expressions and write them here. So integral over AB plus integral over BC plus integral over CD is equal to 0. And what we need to find is integral over BC plus you have this term 2 by 3 u delta w, and from AB we had minus u delta w. So minus u delta w is equal to 0. So integral of v dot dA over BC is equal to, you just subtract and take it on the other side, you get u delta w by 3. Okay, and what was the question? So the question was, we need to calculate the mass flow rate across the surface BC. Now mass flow rate, this what we have found is flow rate V dot dA. Mass flow rate m dot BC is nothing but density multiplied to this, right? So rho integral BC V dot dA, which is rho u delta w by 3. So now you can plug in the values. We are dealing with, I think, water or air. Yeah, we are dealing with air where the density is given to you 1.24. So this is 1.24 kg per meter cube into u into delta. So delta was 5 mm, so 5 into 10 to the power minus 3. So we need the value of u and w. W is 0.6 meter and u is 30 meters per second. Okay, so we have 30 into 0.6 divided by 3. So can you please evaluate and tell me what is the answer? Point 0.0372. Yes. Kg per second, right? Okay. Yes, so this is the answer. And what we should note is that the answer is positive. So what this means is, in this picture, there is excess mass coming in, less mass going out of CD, and hence some mass needs to exit through BC. Okay, so that is the mass balance. There is outflow through the surface BC. Are there any questions about this problem that we just now solved? Yes. Why should it be negative? Yes, that was on the left hand side, right? So you see this is on the left hand side. So I have taken on the right hand side, it becomes positive. This is correct. Yeah. Okay. Any other questions? So I hope you are solving, everyone is solving along with the class. Alright, so if there are no questions, we can move on to the next question for the day. So we have a tank over here, and again, tank is a rigid boundary. So in this tank of 0.05 meter cube volume, there is air at 800 kilopascal pressure and 15 degrees Celsius temperature. At T equal to 0, air begins escaping from the tank through a valve. So there is a valve over here at location 1. and the area across this valve is given to you as 65 millimeters square. The air passing through the valve has a speed of 300 meters per second. So the flow outwards here is known, 300 meter per second. And density is given 6 kg per meter cube. So what we need to find is the instantaneous rate of change of density. Now, just by the question, you can understand that what they have given, first of all, they have given you the density at what location? At this location 1, at the valve. And you have to find the instantaneous rate of change of density. So this is now not the same kind of problem that we were dealing until now. Okay, so the density is changing with time. So let's start by writing the entire equation without making any assumptions. So remember that for conservation of mass, or maybe let's start by writing our Reynolds transport theorem. So this is dou by dou t integral eta rho dv plus integral eta rho v dot d. Control surface, control volume, and this is control mass. So when we talk about rate of change of mass, m dot, in this case m dot is clearly 0. There is no rate of change of mass. So m dot from the control mass perspective, we know it is 0. And if I am talking about mass, then what happens to this equation? Eta is 1, as we discussed earlier. So dou by dou t integral rho dv plus integral rho v dot d. Okay. Now in the previous questions, what we had done, density was constant, so we took density out. This dou by dou t of the entire volume became 0 for a rigid boundary. But now the density is changing, so this term cannot be neglected, and we have to in fact evaluate this term, because the density is changing with time, and it is from here that you will find how the density is changing with time. Okay. So let us solve this equation. What can I say about the control surface term? Yeah, how do I evaluate this control surface term? What are the control surfaces in this control volume? See, in this figure already the control volume is drawn. What are the control surfaces here? One is of course this sphere, and one is this pipe. Okay, so I can say the integral over the control surface rho v dot dA. I can say it is integral over the spherical surface plus this small pipe, after which we have this valve, right? So we have this pipe. Is there any flow across the spherical surface? No. So this is clearly 0. All we have to do is find rho v dot dA, the flux through this pipe. Now along this pipe also, if you see this area, there is no flow in this area. The only flow is from here. Okay, so we can evaluate this. We know the velocity outwards, and we also know that n cap is outwards of this, so n cap is in this direction. So v dot n cap gives me positive, and what are we evaluating? Rho v dot dA. So we have to write rho velocity into area at the location 1. So this is the only term we have to evaluate, and density at this location 1 is given. The density only at the location 1 is given to you, which is 6 kg per meter cube. So I can say 6 kg per meter cube into the velocity, which was 300 meters per second, multiplied to the area. So the area is also given. Yeah, 65 mm square, a very small area. So 65 into 10 to the power minus 6. And as I said, V dot dA, the dot product just gives me a positive 1. Okay. So what is this value? Can you please evaluate and tell me? It's mm square. Yeah. Yeah, it's 10 power minus 6. Okay. 0.117 kg per second. Okay. Is it? Yeah, kg per, yeah, okay, kg per second. Okay, now what about this term? So dou by dou t integral rho dv. So let us write this down here. How do we evaluate this term? Remember, we have to find dou by dou t of rho. Any guesses? Just try and guess. How do we solve this term? Yeah. Okay, at any given time instant, right? Yes. Okay, so at any time t, what I can say is that rho dv integral is equal to rho integral d. So exactly what you said, that density is uniform throughout the volume. Okay, so let me write this. Rho is uniform in throughout the volume. Okay. So now this term becomes dou by dou t of rho v, which is nothing but v dou rho by dou t plus rho dou v by dou t. But there is no change in volume, right? Because this is rigid boundary. So this term is essentially 0. So what are we left with? We have so finally we have volume dou rho by dou t plus the integral over the control surface rho v dot dA is equal to 0. And what this gives me is volume dou rho by dou t plus plus 0.117 kg per second. Is equal to 0. Okay, so what can we say about dou rho by dou t? Dou rho by dou t is minus 0.117 by the volume. So what is the volume of this? How do we find the volume of this tank? So we know the pressure and temperature. Okay, we also know the volume, 0.05 meter cube. So that is kg per meter cube per second. So what is the value? 2.3, yes, but it is minus 2.3. And this makes physical sense because remember what is happening, the fluid is escaping the tank. So if it is escaping the tank, inside the tank the mass is reducing, the volume has remained constant, so obviously the density should be decreasing. And if you have got the value to be negative, that is correct. Okay, so that's like sort of a sanity check. Any questions about this problem? So let us move to the next question. Now again we have an incompressible steady flow and we have two parallel plates. So there is a flow between two parallel plates as shown, and it is uniform initially. But at the outlet, what happens is that the flow assumes a parabolic profile. So you're given all the necessary values. What we need to find is what is the maximum velocity at this central location. So what happens is initially you push in fluid at uniform velocity, but as the flow moves across the pipe, after some time it is going to attain a parabolic profile. Why will it attain a parabolic profile? Because of the frictional effects from both ends, and because of the symmetry of the problem, you are going to have a symmetric. So symmetric in the sense, across this line above and below there is a symmetry, and hence the maximum velocity is going to be at the center location. So we have to find this maximum velocity. So what equation do we use? Do you want to use mass conservation or momentum conservation? What do you think is applicable over here? I think one of you asked this question in the chat. Yeah, how to guess which equation should we use? So Divyanshu, why don't you guess? Should we use mass conservation or momentum conservation? See, we are going to use Reynolds transport theorem, and we are basically saying that there is some quantity conserved, right? So I am basically going to draw a control volume here. Yes, I have considered a control volume, and now you have to tell me what quantity should I conserve across this control volume. Okay, this is simple. Come on, try and answer this. Yeah, mass conservation. So what goes in should come out, because this is an incompressible steady flow. So whatever goes in through this surface will come out through this surface. There is nothing going through the other two surfaces because these are rigid plates. Okay, so we are just going to use Reynolds transport theorem applied to mass conservation. Alright, so dm by dt, which is nothing but 0 from the control mass perspective, that can be evaluated from the control volume perspective. So this is now my control volume. So dou by dou t, control volume, rho dV, plus integral rho v dot d over the control surface. Okay. What about the first term? Is the first term 0 or why is it 0? Yeah, it is incompressible flow and volume we have taken as a constant over here. So we can say this is 0. So then I just have to evaluate this integral, and again we have, let's say, A, B, C, D. So A, B and C, D are the only control surfaces that I have to worry about, right? So we have 0 is equal to integral of rho v dot dA over AB and over CD. Again, I'm going to just take out density because it's constant. So we have to conserve the integral v dot dA. So at AB, what is v dot dA? And at CD, what is v dot dA? That's what we have to find. So at AB, we had uniform velocity, right? So I can say that it is simply u naught into the area. So the area is, let's take unit width into the plane of the paper, and this length is z naught. So u naught multiplied to z naught into the width. Okay, we can keep width w. What about this integral CD? Oh, and by the way, is this positive or negative? It is negative, right? Because n cap here it is in this direction, and here it is in the positive direction. So we should have written negative. Okay. And what about this integral? So we have now a parabolic profile, right? So the velocity is given as az into z naught minus z. So let me write this velocity here, az into z naught minus z into, so dot n cap, that is going to give me positive 1. What about dA? So dA is w into dz. Right, so at any location you consider a small elemental area dz and the width into the plane of the paper. This is equal to 0. So let me just cancel out width immediately. The integral has to go from 0 to z naught. Right, so you integrate all along this surface CD. So let us evaluate this integral and see what do we get. Yes. So if you notice in the question, the value of A is not given to you, right? Z naught is given 4 centimeters, so we can use that. We can use that later, but first let us derive this expression in terms of Z naught. Okay, so the first integral is Az naught into Z dz minus A Z square dz. So this is A Z naught Z square by 2 minus A Z cube by 3. The integral goes from 0 to Z naught. So you can take A common. You have Z naught cube by 2 minus Z naught cube by 3. So what is the value of A? Six U naught divided by Z naught square. Okay, and Z naught is given as 4 centimeters, and U naught is given to you 8 centimeters per second. So what is the value of A? Just evaluate and tell me the value of A. Okay, 300 in SI units. So now what do we need to find? We need to find U max. U max is at the center location, which is nothing but Z equal to Z naught by 2, which is 2 centimeters. So what we need to do is we have to find what is the velocity at 2 centimeters, and velocity is of course given to you in terms of Az into Z naught minus Z. So what is U max? U max is U at Z equal to Z naught by 2, which is equal to A into Z into Z naught minus Z. Okay, so that is 300 into, now Z we have to write as Z naught by 2, so that's Z naught by 2 into Z naught by 2, so the whole square. So this is 300 into Z naught was 4, so I'm going to write 4 into 10 to the power minus 2 square by 4. So please evaluate and tell me what is U max. What is the value of U max that you get from this? Anyone? I hope all of you are solving the question. Yes, thank you. Okay, so 0.12 meters per second, which is nothing but 12 centimeters per second. Okay. Okay, so let us discuss the last question for today. Now, what is given here is there is a spherical balloon. Initially, its radius is r0, and it is being filled through section 1. Okay, so I have not copied the diagram, but let me draw it. have a spherical balloon, which is what is drawn here, and there is a pipe which is inserted into the balloon, and this we demarcate as section 1. Okay, and at any time there is some radius of the balloon. Okay, so radius is a function of time. Now what is given is, initially we start with r0 radius and the balloon is being filled with fluid from section 1, and the area at this location A1 is given to you. So it is denoted as A1. The velocity with which you are blowing in the fluid is V1, and the fluid density is also given to you as rho 1, and this is at location 1, right? So again, this is like the question that we just solved earlier, where you had a tank and fluid was escaping out, but instead now what you have is a balloon and you are blowing into it, so fluid is going into it and the density is going to change with time, and we can expect that the density might increase with time. But because this is a balloon, if it was a rigid boundary, see, if it was rigid like the tank and you keep pumping in air, then the density is going to keep increasing. But in this case, the radius can also change. It is not a rigid boundary, so the volume is going to change with time. Okay, so what is given to you is that the density inside the sphere, inside this balloon, it changes with time, and at any time you can write it as k e to the power t by tau, where tau is some constant, k is some constant. Okay, you have to find the expression for rate of change of radius. So we need to find what is d by dt of radius, which is a function of time. So how do we do this? Now what quantity do we conserve in our Reynolds transport theorem? Again, mass conservation, because whatever fluid you are blowing in from section 1, it has to go into this balloon and it has to stay there, right? So we are going to do mass conservation. Again, dm by dt is 0, and what did we have on the right hand side? So we have dou by dou t of the volume, right? So density into dV, and plus the integral over the control surface for the quantity rho v dot dl. Now again, notice that here we do not have incompressible flow. We cannot say density is constant, so density is changing with time, right? And volume is also changing with time. So how do we evaluate the first term? Let us start with term 1. Yes? Again, rho is constant throughout a volume. Okay, so we have we can rewrite this in this form. So let us write rho dV is nothing but rho v. So dou by dou t of this, we have dou by dou t of rho v is nothing but rho outside dou by dou t of v plus v outside dou by dou t of rho. And both these terms are non-zero because volume is changing, because the sphere is expanding, the balloon is expanding, and density is changing, which is already given to you in the question, right? So I can write this as rho dou by dou t of volume is 4 by 3 pi r cube plus v dou by dou t of density. So density change was k e to the power t by tau. So what does this give? We have rho 4 by 3 pi into 3 r square dou by dou t of r, and this is the quantity that we actually want to find, plus volume, so I'm going to now write the volume in terms of R. Okay, so this is 4 by 3 pi R cube. And what is the derivative of an exponential? So what is the derivative here? Derivative of an exponential is just the exponential function itself, right? So e t by tau into 1 by tau. I hope all of you are following the solution. Okay, now what about the second term? Is there any flow? Yes, tell me. Rho A1 V1, is that right? Rho 1 A1 V1, okay, is that right? Minus sign, very important, right? Because n cap is outwards, right, here at location 1. So this is going to be a negative sign. So term 2, this integral control surface rho v dot dA, again you can write it as integral over the sphere plus integral over the section 1, and this term is of course 0, and this term gives us minus rho 1 A1 V1. So if you sum over 1 and 2 and that is equal to 0, I can rewrite this and you get rho 1 V1 A1 is equal to this expression. So let me take, so we have 3 and 3 gets cancelled, we have 4 pi. So let me write 4 pi out, right? And I'll also take r square common, so 4 pi r square, and we are left with rho dou by dou t of r. If I miss anything, just let me know. Plus, so here we have taken 4 pi r square common, so we are left with r into k e to the power t by tau by 3 tau. Is that right? Yeah. Okay. So we can rearrange this and we get rho 1 V1 A1 by 4 pi r square minus r k e to the power t by tau divided by 3 tau, and this whole thing divided by 1 by rho, the instantaneous density, that is equal to dou by dou t of r. Okay. Right, so any questions about this? Any questions about everything that we discussed today? So this was the last question I had for you. Any questions in the chat? Okay, so that's all we have for today's tutorial. If you have any questions, you can ask next time. Yes, tell me. Yeah, go ahead, Saurabh, please. We have actually done, I think, momentum conservation, right? Okay, let me do that next time. I will, yeah, I'll find some questions. But I think we have done questions on momentum conservation already. Okay, yeah, but I will find some questions for Reynolds transport theorem uh, for momentum conservation and get back to you next time. Okay, okay, yeah, yes, 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 please. Okay, so that I'm not aware of. So that is said by the faculty. But you should expect. No, no. So we do not have any knowledge about how the faculty will set the question. We are tutorial assistants, so we do not have any information about the final examination paper. And but the only thing I can tell you is that you should practice questions from the assignments, and you should expect questions which are very similar to the assignments. Similar to the assignment. So assignment, I think, already has MCQs, right? But in those MCQs also you have to properly solve the questions. You have to do like the way we are doing here in the tutorials. Yeah, so it will be like that. Yes. Okay, so thank you everyone.